Okay, why don't we get started today? So before we get into the lecture, I think everyone saw that the homework has been deadline has been extended to Friday at 5, which I think is probably good in general because that allows you to ask more questions on Wednesday and also office hours on Wednesday. And so I think we'll just generally make that change for the next couple of homeworks, even though the next Friday is going to be Thanksgiving, Friday after Thanksgiving Day. So you're welcome to turn in the homework on Wednesday still if you want to enjoy Thanksgiving vacation. But if there's no objections, we'll allow you to have those extra 2 days to also turn in the homework. So any objections to that? Just shifting the homework due date to Fridays at 5? Everyone okay? All right, I don't hear any objections. So we'll do that. And as I said on the announcements, the homeworks are not intended to have you spend enormous amounts of time. So if you find yourself spending time on it and not making progress, go ahead and post a question on Piazza or come to office hours. That's a good way to save yourself a lot of time. So it's good to spend some time on homework because that helps your learning. If you spend too much time on homework, then you actually get frustrated and you don't learn. So we don't want you to spend too much. We don't want you to bang your head against the wall, you know, and because you're not going to learn that way. So we wanted to sort of challenge you a little bit, but not too much. All right, so everyone okay with that? So make sure you ask for help. We want you to learn, and so ask for help. If you're confused, just ask for help. Okay. And so today, what we're going to do. So are there any? Oh, and then if I forget, someone remind me to go over the project at the end of the class today, just to say some words about the project. Okay. Are there any course-related questions or any sort of burning questions anyone has before we get started? Yes.
I have an MRI lecture 3/2 related question.
Yes, go ahead.
Could you please go over how to determine the signs for KX and KY, and then also how do you determine the sign for a phase, like finding a phase, like how we did on the pre-lecture quiz?
Yeah, that's great. So I will do exactly that because every year, you know, sort of the questions I come up are slightly different. And so this year it seems like the sign is the bigger issue. So we'll spend some more time on that. Yeah. Okay, any other questions? So we'll definitely cover that in multiple ways. All right. Anything else? All right, so let's get started. So after we cover some sort of basic review, we will then get back to case-based trajectories, talk about pulse sequences, and then start talking about sampling, aliasing, and aliasing is relevant to sort of problem 3. Let me just, am I recording? Yeah, okay. And so today, hopefully what we'll do, by the end of the lecture, you'll sort of have a sense of what it is that happens when someone sits down at an MRI console, taps in different parameters, and what's going on behind the scenes in the MRI system. So that's the goal for today, that you should at least have some sense of what types of computations we need to do to make the MRI scan work. So the big concept that we covered last time is that the MRI signal is, if you were basically just sitting there at the MRI console. Let me see, there's a chat question. Can you hear, Professor? Yes, we can hear. Yes, I can hear. Okay, so everyone can hear me. Good. All right. All right. If you can't hear, the best way to get my attention is just unmute yourself and say, I can't hear you, because I will try to monitor the chat, but sometimes it's hard to do that. So if you are sitting at the MRI console, so you have the patient in the bore and they're being scanned, and if you were able to just sit there with an oscilloscope and look at the MRI signal coming in as a function of time, what you would find is that it is essentially, as a function of time, it's like the Fourier transform of that object. So for example, if you were scanning a square, you know, just had a square object, and you were looking at the Fourier transform of, you're looking at the MRI signal as it's coming off the scanner, you would actually see a sync function coming off the scanner. Okay. So it's pretty cool because before I studied MRI, the sync function was just sort of this very theoretical concept that people talked about. But actually, everywhere in the world, the sync function is being used thousands of times right now for both. Later on, we'll see how it's used on the transmit side, but on the receive side, there are essentially sync functions or sync-like functions being acquired as we speak now. Okay. So the idea is that as the signal is coming in, we're getting measurements at different points in k-space. All right. And where we are in k-space is determined by the gradient. So it's given by these two formulas here. And it's essentially, we look at whatever gradient waveform we have, we integrate over time. And whatever time we look at it, we sort of look at the integral that's been accumulated up to that point in time. And that's where we are in k-space. And then we multiply it by gamma over 2 pi just to get the units right. So we're going to talk a lot about how to design those gradients in this course, in this lecture. Let's put that off. Okay, but first let's review a little bit about k-space and talk a little bit about the sign. So a couple of things. One is that if you remember from last time, if I'm at some place in k-space, let me change the color of that to a better color, orange. Then one way, so if I'm at like this point in k-space here, and I draw something out to it, then I know that the pattern is going to be perpendicular to that. Okay. So one thing is I'm just given some pattern, then I can usually tell where I'm in k-space by just imagining drawing the perpendicular to that pattern. So for example, if I was out here in k-space, I'd have this pattern. Okay. Similarly, if you see a pattern, right, like this, then you would have to somehow imagine drawing a perpendicular to that. So that would be like this point out in k-space. All right. So you can go from either k-space to the pattern or the pattern to k-space. Right. And so that's one way of telling you what quadrant you are in k-space. And then the spacing of those, this pattern, so the spatial period, right? Let's say spatial period. So this is another one of the pre-lecture questions, was just simply, if I give you kx and ky, right, then how do you know what the actual spatial period is? And so basically, the formula is fairly straightforward. You just plug in kx squared and ky squared, okay? Basically, Pythagorean theorem, do the inverse, that's your spatial period. And that's really all you have to do for that problem. Okay, so not a lot of these, so the pre-lecture quiz problems, let me just talk to you a little bit about it. Typically, the ones assigned on Wednesday will be a little more, maybe require slightly more time, and the ones that will be assigned on Monday will require less time because you have less time to review. So I'll sort of gauge the difficulty, but they are meant to be, if you understand the concept, they are meant to be answered in 1 or 2 minutes. Okay, if each question, if you really, so for example, this one, if now that we talk about it, you can say, all I do is take kx, ky, square them, take the square root, and do 1 over that. Okay. So if you find yourself saying, oh, this is going to take me an hour to do, that's not how those questions are designed. They're really sort of, if you know which formula to apply, they should be relatively straightforward. So they're not, once again, not meant to make you spend a lot of time, but just meant to help you sort of figure out what the concepts are. All right. Okay. So so that's one of the pre-lecture questions which I wanted to get to. Now let's look at the sign. We're going to look at it in this couple different ways. So here we have 2 patterns. This was actually from one of the, I think probably a 2019 final exam. We used to have final exams in this course, and then COVID hit and we got rid of that. So now we're still staying with projects. Okay. So whether that's good or bad depends on who you are, but just realize that this was like the final exam 2 years ago. You had to say where you are in k-space, and this was just like 2 out of the 9 patterns you have to look at. All right. So let's go through that because I think this might help. So the main thing is that you always come back to basics. You're always figuring out what function are you plotting, and we're always plotting. And you'll be told this explicitly, but because we're looking for something related to the Fourier transform, we're always plotting e to the minus j 2 pi kx x plus ky y, which has the form e to the minus j theta, or let's just call it j theta, right? So really, so that way we just care about what theta is, okay? So we let the theta absorb the sign, all right? Okay, so we explicitly say that's e to the plus j theta. Okay, so all we really care about is the sign. So we know that if I look at the thought sign saying the x direction is just minus 2 pi kx x, if let's say along x, right? The theta is always minus 2 pi kx x, right? So that means if kx is positive, right, and I'm moving along the x direction, right, then that's going to be a clockwise rotation, right? Because the theta is becoming more negative as I move along positive x. So that was one of the questions that came along the Piazza forum yesterday, all right? And similarly, if kx is negative, then as I move along the positive x direction, then I'll have a counterclockwise rotation, right? So if kx is less than 0, then as I move along the positive x direction, it would be a counterclockwise rotation. And the same thing applies for wall. All right. So let's look at this question. So first of all, we look at the period here along x, and let's say the period is, looks like it's 8, right? So it's like from here to here, and that's a spacing of 8. Everyone see that? So then kx equals 1/8, but we have to figure out what the sign is. So is that going counterclockwise or clockwise as I move along x? Clockwise. So we know it's positive, right? All right, now let's look at the y direction. The period here is also 8, I believe, right? So ky equals 1/8, and we have to decide on the sign. So as I move along the positive y direction, which is up now, right? Because you have to look at read these labels, right? So up is positive y. So is that going clockwise or counterclockwise? Counterclockwise, right? So we know that's negative. Okay. So so there was obviously one production quiz problem where there was like a bimodal distribution, and some people picked the plus and some people like the minus, and so that's, you know, if you didn't get that right, that's basically this is the thing that you just need to think about some more. Okay, let's do one more problem just to make sure everyone has it. So let's look at this one here. So here the period is, what is it? Zoom in a little bit. It looks like it's 4, is that right? Okay. So the period is 4. So kx equals 1/4. And is it going clockwise or counterclockwise? Counterclockwise. So we just make this a minus, right? Okay. And what about the period in the other dimension? What's the period in the y dimension? So it's 6, right? Yeah. Okay, so ky equals 1/6. Then is it plus or minus?
Plus.
Looks like it's plus, right? Because it looks like it's rotating in the, well, can we tell? Let's see. Yeah, it looks like it's going clockwise, right? As we move up. So that would be plus. All right. Yes, question.
Could it also be where it does like a full rotation of over extra?
Yeah, it could be, but in general, when you see a problem like that, just pick the simplest interpretation. Yeah. So obviously, there's always a 2 pi unknown, or it could have gone the other way. But then, in general, you know, if you ever see a problem like this in this course or anywhere, just go for the simplest interpretation. Question.
So in the homework, we have some that go from like left, right, and with those, how do we exactly determine?
You mean, what do you mean they go left or, oh, you mean that, oh, so then it basically, it doesn't really matter. If it's a 180-degree rotation, is what you're saying.
Right.
Yeah, so then you don't know which way it is. So then you can pick whichever, then you can just make a note that I can't tell.
I'm asking because this is the one we have to fill out the table for.
Yeah, so the table is, so you actually have to just enter in which one it is, right? So then in that case, you can you can just you can just pick one. And then if you want to be super sure, just add a note for the TA saying, can't tell because it's of high rotation. Yeah. Okay, great. So then there's one last issue, which is related to the pre-lecture quiz is, so everyone okay with this, looking at phasor diagrams? So hopefully this will help you with your homework as well, right? So once again, that homework I think had what, like 9 things, right? And then you have 3 things. So once again, that's something that, once you get it, hopefully it doesn't take you too much time. If you do, like each of those might take a minute, right, to do. So that's 9 minutes, and then adding up the things, maybe is another few minutes for each object. Okay. Yeah.
Can you talk a little bit about what you expect when you find the fix in the sum of the objects?
Yeah. So basically, for every k-space value, right, you multiply the object, right, and then you sum up. The object only has zeros, and then only where it has non-zeros do you add up those vectors, right? So then you would add up all the remaining vectors and get your value. And then along the different k-space patterns, you should see that vector sum change, right? So whatever k-space pattern gives you the biggest vector means that pattern is the best match to your object, right? So then you can even do a sanity check. You can go back and look at that pattern and say, well, does this pattern, of all the patterns I have, does this one look the most like my object? And if it doesn't, then you should probably go back and check your math, right? Because the idea is the Fourier transform is such that if I do a Fourier transform, the k-space value that has the highest value should be the best match to my object. All right, so that's what that exercise is meant to show you. Okay, great question. Anything else? All right. Let's go back and cover one last concept, which was, I think, the question where actually there was sort of the biggest bimodal distribution was the first question, right? Which was like, if you have 1,000 Hertz rotation, and then is it, I think it's like plus 90 or minus 90, whatever. So there, the main concept is, remember, we have to go back to the fact that the precession we're modeling is either minus j omega naught t. Okay. So that means that theta is equal to minus omega naught t. And that's what we're assuming for our MRI proton precession. So in that case, then depending on how much of a cycle you've gone, first of all, it's a clockwise rotation. And just knowing it's clockwise then should let you determine the sign, right? So I've gone like 1/10 of a cycle. Let's say 1/10 of a cycle is, 1/10 of 360 degrees. So that's 36 degrees, right? So if I know I've only gone 1/10 of a cycle, then I know I've gone minus 36 degrees. Okay, because it's clockwise rotation. It means that if in that amount of time, according to the frequency, I only went 1/10 of a cycle, but I did it this way, right? I went clockwise. So therefore, I'm at a negative angle. So theta equals minus omega naught t. All right, so that's how you would determine the sign given sort of how much of a cycle you've gone. All right. In this case, omega naught, and here we're assuming omega naught is greater than 0, right? Because you're just told that you're just given the value. Okay. Now, if I gave you omega naught was minus 1,000, which means it's relative to some other thing, it's minus 1,000, then it would go the opposite way, right? So you can always go back to the basic. You always have to go back to what's the basic definition of what the phasor is to figure out the sign. All right. Okay. Any questions on that before we move on? Okay. So to remind you from last time, the basic MRI pulse sequence is we excite the magnetization with an RF pulse. We apply gradients to move us around in k-space. So in here, the GY gradient moves us along the KY axis, and then we turn it off, and then the GX gradient moves us along the KX axis. And so we play this game, we first move out to some point along the KY axis, and then as we move out farther, the spatial period decreases, the spatial frequency increases, and then we start applying X gradient, so that starts adding variations along the X direction, and so therefore we move out diagonally. So now we're at some diagonal vector in k-space. And then this basically becomes the foundation of our spin vortical sequence. Okay. So the idea is that these two gradients here, their job is, these are called the pre-phasing gradients. They move us out to the initial point. So their job is to get us out to this point in K-space. Okay, they're both negative, so they're going to move us out to this point in K-space. So that area can be negative. It's, even though in real life you can have a negative area, in MRI you can talk about negative areas. Okay, so if the gradient is negative, then that's a negative area. Okay, so both of these guys have negative areas. They move us out to some negative point in K-space. Okay. Then we turn off the GY gradient, so we're not going to move any more along the KY you mentioned, right? We only have a GX gradient, now it's positive, so that's going to move us in the positive KX direction. So now we're just going to cover one line in K-space. Okay. This is what's known as the readout line, okay? Because we're reading out data line by line. Okay. So in general, this will be called phase encoding. Okay, so the phase encode gradient for spin orbit determines sort of where you are in KY, and then the readout just moves you along any line. Okay. So that's the fundamental pulse sequence. And then the way MRI works, at least very basic MRI, we'll get into more complicated MRI later, but this is the way MRI works. You excite some magnetization, you get some spins, and you acquire one line in K-space. Then you wait some amount of time, and you excite magnetization again, acquire another line in K-space. All right, so it's line by line by line. The spacing between RF pulses we'll talk about in a future lecture, because that's something that's not, you know, how far should you space those that time? Turns out it's up to you, depending on what you want to measure. Okay. For now, we're really just going to focus on what data we're acquiring. So once again, if I have a relatively large gradient, it moves us out pretty far in K-space. So for this rep, I get this line in K-space. So each of these is called a repetition, okay? For the next one, you see this gradient is smaller in amplitude, so it's less negative area, so it's not going to move us out as far, right? And then here, I have zero gradient in GY, and so I'm not going to move away from the KY axis at all, right? And I'm just going to acquire the line along KY equals 0. And then I can imagine adding positive gradients now, and that's going to acquire these positive lines. So that's really the spin pulse sequences, which is the bread and butter of MRI. There are other ways of moving through K-space, but I would say the vast majority of sequences use some variation of this, where we're just acquiring lines. And this is, it's called a Cartesian trajectory. Okay, so now let's talk a little bit about sort of, now that we're the basics, the rest of the class is really about how to do these computations, sort of making it, going from just sort of, you know, talking about things to sort of more, what's the engineering that you would do? So if you're an MRI engineer, these are the sort of computations you would sort of have to be at least familiar with doing, all right? So let's assume that you had a gradient that had 1 Gauss per centimeter, and then you turned it on for 0.235 milliseconds. So the question is, where are you in K-space at the end of that? Okay. So, so you just plug in the formula. You have gamma over 2 pi, which let's say is 4257 hertz per Gauss. You have this on for, it's a 1 Gauss per centimeter, and you have it on for 0.235 milliseconds. So therefore, this area is just 1 Gauss times this number here. Okay. And obviously, I've chosen this number here because in this case, it gives me a very nice answer, 1 inverse centimeters. All right. So so then that means at the end of this time, the space in between one period here is 1 inverse centimeters. All right. Okay. So we're gonna do this one together, and then the next one we'll have you guys sort of break out and talk about it just in the interest of time. So here's a very basic calculation you might want to do, because the next one is going to be related to your homework. So I want to spend more time on the next exercise. So I'm going to go through this together with you guys, and then we'll do the next, have you guys do the next one on your own, so it can help you guys with your homework. All right. So this one is, you want to move from the center of k-space to some location kx equals 1 inverse centimeter, ky equals 2 inverse centimeter, using gradients that last for 1 millisecond. Calculate the gradient amplitude that you need to get out there. Okay. And you can assume that gamma over 2 pi equals 4,000 hertz per Gauss. So the calculations are relatively easy. So let's look at that. So basically, I know I have gamma over 2 pi, right? I'm trying to solve for my gx gradient. I don't know what that is, right? And I know I have it on for 1 times 10 to the minus 3 seconds. And I want to move out to 1 centimeter. Okay. So now you just basically it's just simple algebra. Gx equals, I take that over to the other side, 1 times 10 to the 3. And then this is 4 times 10 to the 3, right? So that's equals 0.25 Gauss per centimeter. And so luckily that is one of the answers for that, okay? And then what I could say, well, so if I was doing this on a test, then I would say, well, let me just double check and make sure that this gy equals 0.5 centimeters makes sense, right? Otherwise, maybe it's a trick question, right? So how would I do that? Well, I know that ky, I'm moving out to twice as far in k-space, right? So therefore, it sort of makes sense. I need double the amplitude. So if I thought through that, I was like, okay, that makes sense. All right. Okay, so this is now related to the homework question. So we're going to start off with some fairly simple questions to sort of get things started. So for the first one, so this is what the pulse sequence looks like. So along the gx, you have it up and then down, and it has a value of 10 Gauss per centimeter. Okay. In the gy, it's ramping up to 10 Gauss and then ramping down and then coming down and back up again. Okay. So so the first question is, assume that gamma over 2 pi equals 4,258 hertz per Gauss. The first question is, what are kx and ky at this point in time? Okay, so I'm actually going to use a poll for that, just so everyone. And once again, you're welcome to talk about this. We'll only spend about a minute on this, so it's arbitrary multiple choice. So just pick either. Well, you can pick A, B, C, D, or E, right? So even though it goes through F or G, just if you're on Zoom, if you're not on Zoom, you can just yell it out later. But if you're on Zoom, just go ahead and enter your question. Okay. So we'll do the Zoom poll and we'll supplement it with a hand poll as well here. But if you're in class, you can log into Zoom as well. It'll take about another minute, and then we'll reconvene. Okay, great. So what we're going to do in person, we're going to do an experiment. So I know if I do it individually, no one's going to want to raise their hands. So we're going to do it like they do in Congress, which is very messy. When I say 3, I just want everyone to yell out what they think is, and whatever I hear the most, I'm assuming is the most popular vote. Okay. Yeah, yell out A, B, C, D, or E. All right. You know, at a moderate tone, like don't, you know, like yell it out like this, right? Okay. 1, 2, 3. All right. So the unanimous vote here in person is E, and that also did get 56% of the votes online. So we do have a winner. It's E, and that is the correct answer. Okay. So, and that should be something that's one of those things that you want to be able to just look at a waveform and go, oh yeah, obviously it's 0. Because if I think about the area, any area I accumulate here is canceled out here and assimilate here and here. These sorts of waveforms appear everywhere in MR because we're always balancing out gradients. We're always trying to get back to the center of K-space for a lot of things. So you always see these types of waveforms. In fact, these are called bipolar gradients because they basically are things that have 0 area, but as we'll see later in the course, have very useful applications for things like when you're trying to measure velocity. Okay. All right. So now slightly more challenging. We're going to end the previous poll, but give you a few more minutes. Let's see. To do this next one. So now we want to know where are you in K-space here at 2 milliseconds? Okay. So go ahead and do that and just think about that. And this, once again, we'll just open up the poll for that, and then we'll reconvene in a few minutes. All right. Poll. Yeah, I'm trying to figure out how to end this. I'll relaunch the poll. Okay, relaunch. Yeah, the poll's in Zoom. Yeah. We'll also do a voice poll in here just because it seemed like it worked. Okay. Yeah, feel free to talk with your neighbors. If anyone wants a breakout room, let me know, or you guys can just chat online too, that's fine. So feel free to use the chat feature if you're online. You can people can collaborate online as much as you want. Oops, I almost put the answers. Okay, well, about another minute, so go ahead and answer your question online or get ready to do a voice vote. Okay, so if you're in person, at the count of 3, just yell out what you think the right answer is. So you'll be anonymous because I won't know it's Alabu. yelled it out. So go ahead, 1, 2, 3.
D.
D. Okay, so the unanimous vote here is D, and that corresponds with the online vote, which has 64% of those who responded D. Okay, so that's good. So I think you guys have the hang of it. Let's go through this just to make sure everyone's on the same page. So once again, for this, we actually do have to calculate things because it doesn't go to 0, right? But the easier one to do obviously is this one, right? I mean, just you don't have to think about this one. The area is simple, right? So essentially you're going to have gamma over 2 pi times, what is it, 10 Gauss per centimeter. And it's on for 2 times 10 to the minus 3 seconds, right? Okay, and we have 4, in this case, since it's a book problem from the book, we're actually using close to the right units. So 10 times 2 times 10 to the minus 3, and it's asking you for the closest one. So we just have to get this approximately correct, all right? So this times this is 2 times 10 to the minus 2, right? And then the 10 minus 2, if I applied it to 4258, would give me 42.58 times 2, which I can see is roughly going to be 85, right? Gauss per centimeter. All right, so that would be D, and then we double check. Okay, this says this is about half of that, right? 42 is about half of 85, right? So we say, does that make sense? And then we say, well, yeah, of course, because this is just a triangle, right? And the area of the triangle is half that of the rectangle, so yeah, that makes sense. All right, so that's all you would have to do. So a lot of these problems, I mean, that form is pretty simple. You're just calculating areas, and everyone can do areas, and we'll do fairly simple, waveforms in this class. This problem actually is, probably going to be the more on the end of, the more complicated in terms of let's map out what these waveforms look as a function of time. That's sort of what you have to do for the for that problem, and then we'll sort of draw it out, and then for the problem you just have to sort of put in the units and then also give a mathematical description of what it is. Okay, so if we look at kx as a function of time, so we have 1, 2, 3, 4 milliseconds. We know we start at 0 and we know we end at 0. Okay, so that's pretty easy. And we know that at 2 we've gone to 85, right? So that's here. And then we know we have to get back to 0, so it's just going to be something like that. Okay. The ky is going to be slightly different. So we draw it here. Okay, so now, there's going to be a couple of breakpoints. We know, let's see. Okay, so we know at this point here, right? At 2, we're at 42, right? So we know at the beginning we're at 0, in the middle we're 42, and at the end we're back at 0 again. Okay. So now the question is, what does the waveform look like in between? So initially, I'm integrating a line. So what waveform should that look like? Yeah, parabola, right? So now you go back to whatever grade you learned this in, sometime in high school probably. Okay, so you can have a parabola here, right? Up to 1 millisecond, right? And then what's going to happen? Now you're integrating a line that's going down. So what's that going to look like? Parabola going the other way, right? And so on and so forth, right? So it's pretty easy to figure out what that is. And so you're just asked to give, in the problem, you can just say, this is a piecewise function. So you might say between 0 and 1, the function is this. Between 1 and 2, the function is this. And you can just break it up piecewise and have a mathematical description of it for each chunk. All right. And then the next thing is you're going to want to relate ky and kx to each other. Okay, so that's now more parametric, right? You have to go back to thinking about, parametric plots, right? They're both a function of time, but you're going to have kx and ky are going to have some relationship, right? Maybe it looks like this, who knows, okay? But the hint is obviously kx is pretty much linear with time, right? So that's the hint, right? So it's a fairly easy parametric plot that you have to do. But you might have to sort of refresh some neurons back into, well, what the hell is a parametric plot, right? So it's just two functions, kx and ky, are a function of time. Now you're trying to relate them to each other. But this problem is pretty easy because kx is pretty linear over time. So it's just a scaling factor then. All right. So that hopefully that problem will, you'll learn something, but it won't take you a lot of time. That's the hope. And if you run into difficulties, once again, either come to office hours or post something to Piazza. We want you to learn, but we don't want you to sort of, you know, cause damage to yourself. Okay. All right. Any other questions before we move on? So as an example of what you know, if I have an object, this means that, let's say my object was a very simple square, and we're talking about 2D now. And we know that the Fourier transform of a square is just a two-dimensional sinc function, which means if I put this in the MRI scanner, I would be, as a function of time, I'm going through this line by line by line by line by line, right? So I should map out, you know, when I'm sort of at that bottom line, I probably won't see much. And then as I sort of moving to that peak, I should start seeing hints of that sinc function getting bigger. And then once I'm past the peak, it should get smaller and smaller and smaller. And that's exactly what you'd see if you were at an MRI scanner. Oops, doing that. So this is just a sort of a movie of that. So this is my object here, and I'm just going to be filling this in k-space line by line by line. And then this represents what's along each line. So we'll play this twice. You can sort of see here at some point, take it to the center. Let's see the sinc function, and then sort of dies away. Okay. So this is what the data looks like as it's been acquired in k-space. So play that one more time. Get closer to the peak. First, I start reading in that peak, and then I get the peak, and then sort of goes away. Okay. So really, if I sort of go back and forth here, so see here, I don't really have I've got some stuff in k-space out here, right? I've only acquired lines up to here. Okay. And then as I get close to the peak, now I've acquired data, including this big peak here. And then as I go farther, then I'm just collecting this remaining data out here. And when I'm done, I've collected the two-dimensional sinc function. And I can take this two-dimensional sinc function, inverse transform it, and I get my object. All right. So what we've talked about is Cartesian. Okay. But there are many, because it's just the integral of the gradients, there's many ways you can go through k-space. For example, you can do a square spiral, which you probably do on one of the homeworks coming up. You could do a zigzag, which is a very popular sequence that's used, we'll talk about later, when you want to go through k-space very quickly. And then there's also radial. Okay? You can do radial projection through k-space. What does this remind you of, this acquisition here? Where else have you seen radial lines in k-space? In this class, actually. CT, right? So you can actually make MRI like CT. You can just do radial, and it turns out that there are actually applications for this as well. All right. So one of the cases where you might do want to go very fast is something called single shot EPI. This will be, you'll have a problem on this in the coming homework. And this is a sequence where you start off at one place in k-space and zigzag across k-space. Okay. And this is different from before, because before we said we're going to acquire one line at a time through k-space. This isn't like saying, I don't want to wait, I'm greedy. I want to be able to do images very quickly. So in this case, you have one RF pulse, and then you just try to zoom through k-space as quickly as possible. Yeah. So this is very useful for any time you want to do a very quick imaging acquisition. See, there's a question online. Oh, CT scans, right? Great. Okay. So in the interest of time, I'm going to skip over this. You can watch this video. It's sort of fun to watch. It's posted in Canvas. The idea here is that the gradients can make sounds because they are basically vibrating at audio frequencies. So in this video, you're going to see how you can actually play any music you want through the gradients. So the magnet is actually playing the music. It's like a big speaker. You know, you could if you want to, you could hook your iPhone up, play any music you want through those speakers. It's a very expensive speaker, $3 million speaker, but you could do it. Nonetheless, you can even have, as you see in this video, you can actually have the magnet talk to the person. And so it's sort of cute. I mean, people talk about using this, and certain clinical scanners do use this to prompt the subject, but it's I think probably more cute than actually used that wide. Okay, but in the interest of time, you watch that video on your own. All right. Because I do want to cover case-based sampling, because now we're really getting to the heart of the matter. How do you do MR imaging practically? Okay, because essentially you've got case space here, right? And there's two questions we need to answer: is how far out in case space do we need to go, and then how finally do we need to sample case space? Okay, because both of those things take time, and the more time things take, then they tend to be more expensive. Okay, and also in a clinical environment, time is also related to survival, right? If you have someone who's sick, you may not be able to. I mean, if you have a research subject, you might say, lie in the scanner for an hour and don't move, right? But if you have someone who's just had a severe injury or is not feeling well, you may only have 10 or 15 minutes to get your data before they start moving around, or they just can't bear the scan anymore. So there is an emphasis. Ideally, if you talk to most radiologists, what they'd love is to have like a 10-minute protocol where you just go in for 10 minutes, get all the scanning you want. As opposed to now, it's more like 30 minutes to an hour. Okay, so there is this desire for radiologists to go faster. Okay, so that means you want to collect as much data as you need, but no more. Because if you collect data that you don't need, you're just wasting time. Okay. So the idea is, given so the parameter we talk about is FOV. So FOV is like, this is how big my object is. FOV stands for field of view. Okay. So one parameter you're going to put in the MR console's field of view. The other parameter you're going to put in is your resolution. That's essentially what your voxel size is. You might say, I want 1 millimeter resolution, or I want 2 millimeter resolution. Right? This is sort of like, when you buy your iPhone or your MacBook Pro, how many pixels you want, right? And based on that, we're going to use those to determine how far out in case space you want to go, and also what's the sampling in case space. And this is sort of similar to some of the images you should get for problem 3 of the current homework. So for example, here I have my object, I have my case space. Here, what I've done, similar to what you'll do in your homework, is I've just zeroed out every other line in case space. As if I didn't, it's saying I don't have that data. Just skipped over every other line because I want to go twice as fast. Okay, because especially if you're using spin warp, every line takes a repetition. So if you can skip every other line, you can go twice as fast. But the problem is, if you just do that without thinking about it, you're going to end up with an image like that. Okay, which for obvious reasons is not desirable, right? I mean, if you went to your doctor and you saw these as your scans coming back, you'd be like, no, please do that again. Okay. Similarly, if I skip every other line in KY, I get aliasing like this. So the image is overlapping itself. And here I skip every other line in both directions, and you sort of see there's lots of overlap. Okay. So we definitely want to figure out what is the design criteria to avoid that overlap, because we want to minimize aliasing. Right, so the way that aliasing appears in MRI is things appear where they're not supposed to appear. Okay. So we're going to talk a little bit about why that might happen. So one way to think about it is, if I don't sample finely enough, if I take too big of steps, for example, as I'm going along, then what happens is a spin here in one part of the object does the same thing as a spin here. Okay. And because the only thing I do in MR, I can't look at individual spins in MR, because I just have that coil that sums up everything, right? That's the vector sum, right? So if two things, so basically the idea is, for example, if I have two people in the room, right, and I just have a sound recording here, right? If you're saying exactly the same thing, and I'm just summing it up, I can't tell where you're from, right? So basically, if you were all saying like MRI is really great, two people in the room saying the same thing, and I just listen to it here, maybe I can maybe tell that there's more than one person, but I don't really know where it's coming from. I just have one microphone here. Whereas if you said MRI is great and you said MRI sucks, then at least I could know, well, you know, there's two different people in this room, and maybe I can tell where they are. Yes.
That image also, I don't know if you talked about earlier, it could be narrowed too high.
Yeah. Yes, exactly. That's some. It's going to be related to that. Okay. So let's look at this. So this is trying to motivate that. So basically, these are all the spins, right? At this point in time, all the spins look the same, right? They're all in the same. If this is the only data I had, I have no way of differentiating the spins. Now let's say I had some gradients, so the spins start getting out of phase. Okay. But let's say this is all the data I had. So all I said is, and notice at each point in time, I'm just going to get the vector sum, right? So these are spins. If you look at sort of these two spins, right? Because of how I've sampled, they're doing exactly the same thing over time. So from the point of view of how they enter in the vector sum, they're coming in the same way. It's like they're saying the same thing. Okay. So I can't really differentiate those two spins. So basically in MRI, this means I would say this spin and this spin have the same location. So that's what aliasing is. So how would I fix this problem? Here this spin went from this point to this point to this point. This spin advances pi each time, right? So this spin is going probably plus pi each time. This spin is going negative pi each time, right? Because plus and negative pi are the same, I can't really tell them apart. So what could I do to differentiate these two spins? Because one's going clockwise, the other is going counterclockwise, but I can't tell because I'm sampling too coarsely, right? So what could I do to tell these two spins apart? Any ideas? So if I waited enough time that they've gone pi and minus pi, what could I do so I see them so that they're at different angles? If one's going clockwise and one's going counterclockwise, what should I do? Should I wait longer, or should I sample more coarsely, or should I sample more finely? Any thoughts? So it's sort of like if I have sample. So this I'm taking means more finely, right? Okay. So that's exactly the solution, right? I should sample more finely. So now this spin here goes 90 degrees, and this spin here goes minus 90 degrees, right? So now I can differentiate. One's going clockwise, one's going counterclockwise. And now these two spins are going to come in differently into the MRI equation, right? And because they have a sort of a different signature, it turns out I can unravel that in my inverse Fourier transform and figure out where they are. Okay, that's the basic idea. We'll skip over this example for today, and we're going to really now review the process of sampling, which Professor McVeigh touched upon, and so we're going to be reviewing a little bit of that to get to the sort of the mathematical result that we need. So sampling is essentially anytime we're taking a continuous waveform and converting it to digital samples. So this is basically all of our lives now, right? Everything is pretty much digital, and so as compared to say 50 years ago, where most of our life was analog. Although I've heard that vinyl is coming back into vogue, but even vinyl now, I think it's a vinyl thing, but then they convert it to digital and play it through some speakers, so it's sort of hybrid. Okay. But in the old days, it really was analog all the way. You had the needle vibrating and everything was analog. Okay, so remember the function we need is what's called the cone function, which is a bunch of Dirac delta functions that just pick out the values of the function. And it's a sum of these delta x minus n's. And so these are spaced one apart by definition. But what we really want is a scaled cone function, so we can vary the spacing. So we can take cone of x over delta x, and this is going to give us a bunch of cone spaced delta x. Now, because of the properties of the Dirac delta function, this actually leads to this additional scaling term delta x, For the purpose of this course, just ignore leading scaling functions. You know, we have so much else to keep track of that we're not going to worry about that. Okay, all I really care is about the spacing. Okay. The other key result is the comb function has a very nice Fourier transform. Is that the Fourier transform of a comb is just another comb. Okay. And so if I take the Fourier transform of a comb that is spacing delta x, I end up with a comb in k-space that is spacing of 1 over delta x. And so that's the most important thing to realize, that this is just an example of the scaling theorem. If I make things narrow in one domain, it's going to spread out in the other domain. Okay, so if I make delta x get smaller, 1 over delta x is going to get bigger. That's the main thing you need to keep in mind. So that's shown here. Delta x is here. If I do the inverse Fourier, if I do the Fourier transform, I get a spacing of 1 over delta x in the frequency domain. So let's relate that to MR. So imagine I had my object with just a direct function. And I know the Fourier transform, it's a sinc function. And if I had all the time in the world, I could just sample it as finely as I wanted to. And I could sample it from minus infinity to infinity, right? But if I did that, the subject would be dead, right? Because it's, you know, that's a long time to scan. So I'm going to limit how much I scan. I'm going to cut off the sinc function. And in addition, I'm going to sample it. So I'm only going to sample it here at different points in space. One question is, for example, how finely do I need to sample the sinc function to be able to recreate it? Okay. So there again, the Fourier sampling we realize is basically this is just saying that, you know, the spacing here is this delta kx is our sampling. So basically in the Fourier domain, so far we talked about delta x leading to spacing of 1 over delta x. So that's what sampling would look like if we were doing an image domain. So we can take the same picture and say, well, actually in MRI, we're not sampling in the image domain. We're sampling in the Fourier domain. We're sampling in k-space, right? So all we do is say, okay, now the spacing I really care about is delta kx. Right? What's my spacing in kx? And then, so what that looks like is, I'm going to have this thing, and if this is my spacing delta kx, and this is my sampled function in k-space, it turns out if I do the inverse transform of this, I end up with this. So this is the Fourier transform of this sample function. And you can sort of see it's my original function. Okay, so this sinc function is the Fourier transform of my object that I care about. Okay. And here we're going to get into, I've multiplied by a comb function with spacing of delta kx in the Fourier domain. Therefore, this says, anytime I multiply in one domain, I have to convolve in the other domain. Okay. That means I take my object and I convolve it with another comb function. Now the spacing, if it was delta kx here, the spacing is be 1 over delta kx in the image domain. All right. This means I'm going to, and then remember, a convolution with a Dirac delta function just takes your object and shifts it to the location of the Dirac delta function. That means that when I sample in the k-space domain, it takes my object and just moves it and replicates it. And replicates it with a spacing of 1 over delta kx. So now we start to see, oh, okay, well, that just means that if I have these replicas, I just want to make it so that they don't overlap with each other, right? Because if they overlap, I'm going to get aliasing. So I want to set up, so if you can sort of see, if delta kx is too big, right, then 1 over delta kx gets smaller. So I'm going to have a lot of overlap, right? So I've got to make delta kx big enough so that 1 over delta kx is wide enough that I don't get overlap of my image. Right? So that's the basic idea. And that is simply the Nyquist condition, okay? So at an MRI scanner, you will specify the field of view, right? Because depending on what you're going to image, you know, if you're going to image a tiny thing, you don't want to specify a big field of view because then that otherwise it's going to require too much data, right? You're wasting time. So you typically pick a field of view that's just big enough to cover the imaging volume you care about. And once you do that, then you know for any delta kx, the spacing is going to be 1 over delta kx, right? So you just want the spacing of the images, 1 over delta kx, to be bigger than the field of view. Okay? And because of the spacing is less than the field of view, that means areas in the object can overlap. That's the Nyquist condition. So this is the case that aliasing occurs when that 1 over the delta kx is too small, such that now those replicas are going to overlap with each other. Okay. So this is a part where it requires prior knowledge about the object you want to image, right? Because if you have to know, okay, this is the size of the object I want to image, and based on that, I'm going to specify the field of view I need, and then the MRI machine can calculate the delta kx. So this is an example that would happen, sort of a trivial example that would happen if I didn't do the aliasing, the sampling correctly. So this is my function here in k-space. And now let's say delta kx equals 1. So I'm going to get this sample, and then I'm going to have zeros everywhere else. So now my representation of the sinc function is just this, right? I only get 1 point. And that's a delta function, right? Remember the transform of a delta function is 1. And that means that all these replicas just line up next to each other, these rect functions, so I get 1 everywhere. Okay, so that's a trivial example of sampling. Okay, we can also have a 2D cone function. So in k-space, in NMR, at the very least, we'll talk about 2D imaging. It's the same thing. I can have a comb xy, which is comb x times comb y. I can make the spacing so delta x and delta y. And I can also have the spacing being, so if I did that, it would be 1 over delta kx, 1 over delta ky in k-space. Let's see, what am I doing here? Okay. So this is my sample. So basically this is the function I want to have. This is my Fourier transform here. And this is just saying I'm only going to take samples every delta kx, every delta ky. Okay. And so this represents what's happening in sampling. And so let's look through what that means. That means this is my object here. Okay. This is its Fourier transform. Okay. I'm going to sample that with some spacing delta kx in this dimension and some spacing delta ky in this dimension. So you notice over here, I basically have a sampled version of what's over here. Okay. So this is what I'm doing in the MRI domain. I'm getting a sampled version of my desired 2D sinc function. Now in the image domain, I have a rect function because this is the Fourier transform pair. So this rect function now can convolve with the Fourier transform, inverse Fourier transform of this guy, which is another comb function, but now the spacing is 1 over delta k. Okay. So I'll have 1 over delta kx in this dimension and 1 over delta ky in another dimension. Remember, if I convolve this with delta functions, it just moves this object to each delta function, and therefore I'm left with these replicas. Right. So that's the picture you want to have in mind when you're thinking about sampling in MRI. So that leads to what are called the Nyquist conditions, right? And so this is the first design equation we're going to have in MRI, which is that we want 1 over delta kx to be greater than FOV of x, and 1 over delta ky to be greater than FOV of y. Now, typically by convention, the design is such that you can always just, if you're asked to do a problem, you can just find it you just make that, convert that greater than to an equal sign. Right? It has to be greater than, but you can just set it at the limit, make it equal. Right? So if you're given an FOV, you can just take 1 over the FOV, and that's your delta k. Right? Okay, so let's do a simple in-class exercise. Once again, we'll open up the Zoom poll. So this is a multiple choice question. So take a look at this, and based on what we just talked about, here's the question. This is your object. It's cosine 2 pi through x plus 2y, x over 3, vector y over 4. So you're asked to determine what's delta kx and what's delta ky to avoid aliasing. Right? So go ahead and we'll give about let's say about 2 minutes to think about this, and then we'll review. Give it another minute. Just go ahead and submit your best guess, and then in class, we'll do it in class. Voice poll. Okay, so why don't we sort of regroup, and at the count of three, if you're in this classroom, at the count of three, just yell out what you think is your best guess, and I'll try to listen and see what the majority says, okay? Here we go, 1, 2, 3. Okay, so I hear like an A and then C, G, okay. All right, so that's useful information. Okay, that's what I like integrating the answer. Okay, so online, this is all, it's very similar, right? A got 38%, C got 63%, and D got 13%. So remote and in-person, very similar results. Okay, so let's take a look at that. So this is an imaging class, right? So whenever my suggestion is always just draw what you're talking about, because we're talking about imaging, so you might as well draw and know what you're talking about. So let's draw what this looks like, right? So how big is this along the x direction? It's rect of x over 3. So what's this? What's the width of it in the x direction? 3. Yeah. Okay. Nice. 1.5 to 1.5. So it's got a width of 3 in the x direction. What's the height of it? How big is it in the y direction? 2. Okay. 4. Okay. It's 4. So it's so actually, here's where it's useful to remember some very simple rules. The width of a rect function is just given by the denominator, like rect of x over a, the width is just a. Okay, so that's useful to remember because that will save you a lot of time, right? Rect x over w just has width of w. So that's a useful thing to remember, because otherwise, if you think about it, you might make a mistake or whatever. So just remember that's a fact. So that's the thing that we can say. So it has a width of 3, height of 4. Cosine 2 pi through x plus 2y. Do we really care what that is? No, I mean, it's something like this, right? Whatever, right? But we don't care, right? Because it doesn't determine the extent. So this is like a trick question, right? That cosine there is meant to like confuse you and go, oh my God, what's this, right? Now later on we'll have to look at it, but now we can totally ignore it, right? Because it doesn't determine the extent of my object, right? So I can say FOV of x is what? What's my FOV in my x direction? 3, yeah. And what's FOV in the y direction? 4, yeah. So that means that delta kx should be what in the kx? Equals what? 1 over the FOV, right? So 1/3 delta ky is 1/4. So that's all we were looking for. Okay. So once you get the hang of it, you sort of see this. These are the sorts of questions you can answer like just by looking at it, right? Okay. Any questions before we move on? All right. The next thing we need to talk about, so we have about 10 minutes to go, so we're going to talk about windowing, and then we'll talk about the project. All right. So sampling was how far are the samples in k-space. Windowing is how far out do you go in k-space. Okay. So sampling was related to FOV, how big is my object? Windowing is related to resolution. How clear do I want my object to be? You know, what's my pixel size? Okay, so that's the thing to remember. And the key is that windowing means this. I have my Fourier transform, and let's say the sinc function could go on forever. But I say I don't want to get things forever, so I'm going to window. I'm going to multiply a function w that just collects data inside some window. All right. That means I'm going to take my object and I'm going to involve it with the inverse transform of my windowing function. So here's the basic picture. This is my object. Okay. and this is Fourier transform. Right? Well, let's say I don't have time to collect this whole Fourier transform. I only want to collect data in some little square. Okay. That means I'm multiplying the Fourier transform by this square. So all I collect is this data here. Right? I don't have time to collect all data, so I just want to collect data in some square. So I've multiplied in this domain. That means I'm going to convolve in my object domain. So it means I have to take my object and I have to convolve it with the inverse transform of this rect function, which is a sinc function. Okay, so this is why rect and sincs are everywhere. So you want to get used to them. So that means I'm going to take this object and convolve it with this sinc function. Okay, that means you can imagine taking the sinc function and popping it, replacing every point here with a sinc function. That's going to end up blurring out my image. Okay. So as we talked about before, the inner part of K-space is sort of doesn't have the details. And so this is now showing mathematically what's happening. You're basically taking your object and you're blurring it with the sinc function. Okay. So that's just shown here. So here, if my window is a rect with a width of WKX, and in the x dimension, and a width of WKY in the KY dimension, right? That means that in KX space, I've just got a window with WKX and a window WKY. Okay? So here's where what we just talked about is very useful. I can just look at this and say, well, the width is just this, right? I don't even have to think about it, right? Just look at this denominator. And that means that I can take the inverse transform of these guys, and it turns out that this is just a sinc and another sinc. And so that means in the image domain, I take my object and I convolve it with this two-dimensional sinc function. So now what we want is we want to look at these sinc functions and sort of come up with some sort of approximation of, given a sinc function, what's my resolution? So it turns out that what we can do is define the effective width of any function, which is basically effective width is just given. So this is my sinc function, right? And has some height 1. So what I'm asking for is what rectangle has the same height and area as my sinc function, and ask the width, and that's the effective width. Okay. I can go through this. I can take advantage of the fact that the area of any function just is the value of its Fourier transform at 0. So I can go through that and figure out, oh, that just means that the effective width of a sinc. So this is a sinc WKXX, right? So let's look at that. Sinc WKXX has its zeros when x is equal to an integer. Okay, so that means x equals n over WK sub x. So the first zero occurs at 1 over WKX. Okay. So it turns out that if you know where the first zero is, that turns out to be the effective width of the sinc function. And so that's what we're going to say the resolution is. So the resolution given by a sinc function with the first zero 1 over WKX is given by its effective width, which is also 1 over WKX. That makes sense. If in Fourier domain, I make this WKX to get bigger and bigger and bigger, right? 1 over WKX gets smaller and smaller and smaller. So the more data I collect in the Fourier domain, the narrower that sinc function becomes, right? So my resolution gets better. Conversely, if I collect less data in Fourier domain, WKX gets smaller, right? Which means 1 over WKX gets bigger. My effective width is bigger, my resolution is worse. Okay. Let's skip over this for now. So let's do a windowing example. So this is just sort of giving you sort of arguing why that WKX sort of makes sense. So this is showing you basically what happens if you have two direct delta functions. You're convolving each one with a sinc function. Okay, in this case, WKX equals 1. So we're right at the limit. These are spaced 1 apart. And so these are, ideally, these are two things I'd like to separate, the blue and the green, right? But they sum up to just give me this one red curve. Okay, so this is what I would see in my image. I would just see this one thing. So therefore I have originally I have two things, right? But now they've summed up to just give me one peak. So I've lost my resolution, right? I can't differentiate these two things from each other. And this is where WK equals 1 and the original spacing was delta x equals 1. Okay. So what that means is I need to, WKX is the limit where I can't tell things apart that are spaced at that resolution. So I need to make WKX bigger. Okay. So now you notice these sinc functions get a little narrower. And so WKX equals 1.5. They sum up to give this curve here, right? And so it's not great, but if I had enough signal noise ratio, I could tell these two peaks apart. Okay, so that's saying that now I have the resolution to tell these two things apart. And if I go out even farther in case space, now those sinc functions are much narrower. So then the overlap is quite easy to tell those two sinc functions apart. Okay, so that's why the width of your sinc function determines your resolution, right? If that sinc function is too big, then two things that are spaced closely together will just merge into one thing. So you've got to make that sinc function narrow enough such that you can tell them apart. So the overall process of MRI involves both sampling and windowing. So let's just go through this in the last minute or so. So this is my object here. Okay. This is its Fourier transform. This is what I collect in MR. I'm going to sample that Fourier transform. So I'm going to multiply by this cone, and I'm going to multiply by a rec function. That's windowing. Okay, so this is sampling. This is windowing. Okay. And so you notice I'm going to get only data in some inner volume here, and it's sampled. Okay. So I've done multiplication in image domain, so that means I must be convolving in my. I've done multiplication in the Fourier domain. So that means I have to do convolution in image domain. So I convolve this object with this, which gives me all these replicas. And then I take each of those replicas, right, and I convolve it with this sinc function, which is going to blur out each of those replicas. So I'm going to end up with blurred replicas of my original image. Okay. But as long as these don't overlap, I can always just take the center one out, right? And that's going to be my image. So by definition, even though you get these replicas, in MR, you just get the center replica. As long as it's not overlapping any of the other images, you should be okay. So that's all. We'll pick up on this on Wednesday. We're at the end of our time now, so let me just say 1 minute about the final project. So is it visible? Can you guys see the final project? Okay, so it's posted. So go ahead and read through the PDF. It's pretty self-explanatory. So you have until next Monday to sort of form your groups and pick a topic. If you have questions, feel free to ask me. But the idea is the description of the project is just for me to give you some feedback. Like I'll just say, yeah, this is enough, or it's too much, or maybe think about more, just to give you feedback to sort of help guide you in the project. All right. So any questions about that in terms of timing? Okay, so I'll stick around here for questions, and also if anyone has homework or other questions, I'm happy to answer them. Okay, otherwise, see you on Wednesday.
Professor, quick question for the homework. So I know you mentioned that there'll be a couple more homework. So there'll be one more uploaded today. You're going to upload one more homework today for next week?
No, the homework for next week will be uploaded on Wednesday.
Okay.
There'll be at least 2 more homeworks. And if there is a third homework, it'll be very short homework because we don't want, we want people to work on their project. So in general now, the homeworks they'll still come out on Wednesday, but then they'll be due the following Friday.
All right, perfect. Yeah, thank you.
That just gives everyone an extra couple days to get some help if they need it.
Sure, thank you.
Sure. Okay. Any other questions online? Okay, well, let me just end this. Oh wait, there's something in the chat. Okay, all right. Yeah, the other question? Let me just stop this recording then.